I'm Paul Jersinek from Kalamazoo, Michigan. So I should have a slide up for this, but if anyone is from the Michigan area, you know what I'm going to do. I'll put my hand up. And that's Lake Michigan, that's Chicago, that's Detroit, and I'm about there, about 35 miles from the big lake, as we say. And by the way, all the apple trees are in bloom when I left, and it looks like white for literally 50, 60 miles in all directions from where I live. So it's just beautiful. And I think we might have one more frost. 2 weeks ago, we had 8 inches of snow. So, okay, so the subject of the talk here is shifts in target isocenter coincidence with couch rotation. And so that'll make a lot more sense in a few minutes. But this is really the summary of the talk. Where are we in three-dimensional space with a target? And then really, can we stay there? And now most of this talk is not really going to be about patient motion, but it's going to be what physically happens in the machine when we rotate the gantry and so on, and more importantly, what happens when we rotate the couch. So here we go. So the conflicts of interest, first off, I really don't have any. I did not receive funding for this work. However, I do thank the Vision company for supporting my chance to get out here. So they did pay for my costs for the travel. And I would like to acknowledge 2 people in particular. Casey Fitzpatrick is a radiation therapist at our center, and she is just a clever, relentless therapist. She really likes to understand what's going on. And I like to say this: she forced me to stop drinking the Kool-Aid and to study this particular issue thoroughly. So Mike just mentioned hyperventilation, right? And when we were first doing stereotactic radiosurgery and using the Align RT method, I did have a number of ventilation episodes. We also do trigems with a cone, but when you start, I should say, like almost 15 years, I use the head frame, gamma knife and everything. And when you take that head frame off and you look at a patient's face and their skull and you're trying to hit a target that perhaps is 2 or 3 millimeters in diameter, it tends to ventilate. You do ventilate at that point. And you give 80 or 90 gray and you're within 3 or 4 millimeters of the brainstem. Tends to keep you up at night. I want to also thank Ben Vaghorn, who I know is here, maybe not in this session. Ben, if you're here, thank you. I sent a lot of my early data to Ben, and we had lots of emails, and he encouraged me to keep measuring. So thanks, Ben. So for stereotactic radiosurgery, these are the questions. This is really maybe the most important question in terms of a physicist. Where's the Linac radiation isocenter in space? Oh, it's where the lasers come together. No, it isn't. It's almost there. And can you place the tumor at that isocenter once you figure out where it is? So again, where in space? And then again, can you keep the lesion there or the patient there? So this is setup and positioning. This is a lot of physics work, which I'll talk about. And then keeping the tumor at the radiation isocenter, of course, is immobilization. And for the Vision RT community, it's monitoring live, well, about 8 times a second. You're monitoring where the patient is during the treatment. And then, of course, always with a physics discussion is, well, what's the precision? What's the accuracy of these answers? So here we go. So some facts of life. The accelerator MLC, that delimits, in our case, the radiation isocenter. If you're using cones, of course, it's the cone collimator. And the radiation isocenter is in the center of this field. the collimator rotation axis passes through that MLC field, and it's after MLC initialization every day that, in fact, you establish that the MLC field, where it is with respect to the rotation of the machine. And then finally, the radiation isocenter is somewhere on that line where the collimator rotation occurs. One would hope where you expect it to be, but there's some interesting things that occur. So that's some facts of life. And in a perfect world, this is what it would look like. The rotation axis of the gantry, collimator, and couch all would be at one point, and no matter what angle you put the gantry or the couch, it would stay at that point. However, as you all know, this is not a perfect world that we're living in. That's the way it ought to be, but that is not, in fact, what happens. So MLC collimator centering, again, that's important. The leaf motion must be centered on the collimator rotation axis, and that, fortunately, is an almost automatic process. You do an MLC initialization. In our case, it occurs every morning in our clinic, and these leaves are centered with respect to that collimator rotation axis, and it is within, at least on a true beam, 1/10 of a millimeter. The MLC leaf edge, in fact, is the reference object. That's what sets the field, if you're using MLC as your delimiting collimator. So where in LINAC radiation is that isocenter of radiation? Where is it in space? So this is the toolbox of a physicist. For decades, it is the Lutz test. So I'm going to spend a fair amount of time on what the Lutz test is in 2019. It's different than it was 30 years ago in the sense that we just don't use film. But the Lutz test is a radiation image test of where the position is of the radiation isocenter. It's based on radiographic images, compares those images of something of known position, the MLC edge, to something that you're testing, which is a test object. And in my case, this is the test object. You can buy lots of things. I just built one. My test object is, in fact, a threaded rod that has a plastic tube on the end. And inside of that plastic tube, I put a 4 millimeter diameter steel sphere. And the Sarabin and the styrofoam cup, that's just a weight, so I can put it on the end of the couch and keep it there. So you can buy things that are real expensive. This was about $1.20 at the hardware store. Oh, and a few hours of playing around. I like to build things. So the Lutz test, the steel sphere is positioned, and I got a red line here. Oops, I got a red line here, and it's an important one. How do you position that steel sphere? I mean, you got a big room to put it in. Well, the left-right is with the collimator reticle, gantry 0. But when you go to do sup-inf, and this will make more sense in a couple of slides, you go to gantry 90, and you use the collimator reticle again. But it's not at 0 degrees. There is a difference, sup-inf, between what happens at 0 degrees gantry and what happens at 90. And then finally, ant post is also done at gantry 90 with the reticle. The sup-inf position is set at 90, not at gantry 0. And the reason will come up soon. Well, this is what one of the Lutz tests looks like. A couple of things here. This is gantry angle 0, gantry angle 90. Clearly, there is my sphere. By the way, I used the steel sphere. There are a lot of ways you might do this, but that gave me good contrast in my imaging. Probably lead might have been better, but steel spheres were BBs, not BBs, but ball bearings you can buy in a hardware store, so it was easy. And you can see the MLC edges. The other thing you can see, of course, are the pixels. And when I show some figures later on, some graphs, you're going to see some error bars. And the error bars really are telling us, I can only set this up, okay, with the precision of one pixel. The position of the MLC edge with respect to the sphere center is determined, and I use an open piece of software. You can go get it on the internet. It's called ImageJ. And it's free, and it really works well, and it gives you a way of taking an image and finding out where the center of, in this case, a square or a sphere is, and then comparing the centers. And that's used throughout. This happens to be a sup-inf direction, gantry angles, you can see here rotating around. This is on a trilogy, and this is the MLC, how the MLC moves as you rotate the gantry with respect to a sphere in space that's stationary. You don't go bump it with your arm or anything. It's stationary in space. But the MLC collimator is not. It rotates with the gantry, and it moves. It's not perfect, and in fact, this is how it moves. You can see at 0 degrees, that MLC edge is more superior, and when you get to minus 180, it's inferior. And there is a motion, and you can see at 0 and 90, the sup-inf motion is very within the error bar at being in the proper position or 0. So I want to go back a step. That's why the sup-inf position is set up at 90 degrees. And this is actually what's happening as you rotate your gantry. It's sort of like a teeter-totter, and it, in fact, is moving in space just due to gravity. So that explains, at least my explanation of why you go from superior to inferior as you go from 0 degrees to 180 degrees. You actually shift, in fact, the way your gantry is wobbling on the teeter-totter in space. This is the motion of that MLC in the left-right direction. That's also being measured with the LUTS test. And you can see for this trilogy machine, in fact, it's really good. It's plus or minus 0.2 of a millimeter. By the way, the error bars, again, that is the pixel error in the image I'm using to do the analysis. I can't do any better than that. And that's what those error bars are representing. They also represent something else. It's not clear from this, but I did these measurements again and again and again. So there's actually dozens of measurements that underlie these error bars, beside the pixel errors. And then finally, here's an ant post, and it also has about a plus or minus 0.2 of a millimeter change as you rotate the gantry. And again, this is a trilogy MLC with respect to the sphere. So these graphs indicate that the radiation isocenter does the following. It moves with gantry angle. It is not a stationary spot in space. And the motion for the trilogy is somewhere less than or equal to about 0.4 of a millimeter. And I believe the largest motion, which is sup-inf, is the gantry tipping due to gravity. This is a true beam. And you can see here the sup-inf motion of the MLC is smaller. In fact, it's quite a bit smaller. Well, I'll give you some summary at the end. But it is a smaller variation, but it's basically the same. Superior at 0 degrees, inferior at 180. And this is the left-right direction for MLC true beam. And then finally, this is the ant post, and it's almost perfect within the error bars. So here's the summary slide. The trilogy, sup-inf, plus or minus about 0.4 of a millimeter. True beam, sup-inf, 0.2 of a millimeter. By the way, we have one trilogy. We have 2 true beam machines in the clinic, and this is typical of the true beams, both true beams. Ant post, 0.3 of a millimeter, 0.2 of a millimeter, and then finally left-right, 0.3 and 0.2. So the radiation isocenter, no matter what machine we're looking at, is the average position of all of those shifts of the MLC. So you don't have a point in space. Like I said, this is not a perfect world. In fact, you have a ball with 1 or 2 standard deviations. Of course, the ball will get bigger with 2 standard deviations. And that ball has a dimension. The diameter of that uncertainty is certainly somewhat smaller, that quite a bit smaller in the sup-inf direction for a true beam, but it is definitely not a point. So that's the LUTS test, and that tells us about radiation isocenter. But now we're going to change perspective. We can also use the Lutz test to tell us what happens when we rotate the couch, and which is really the purpose of this talk, because what we found when we were doing stereotactic setups is we would have a 0-degree couch, everybody's happy, we do a cone beam CT, we have a reference image in Align RT, and the patient looks perfect. Of course, they move a little bit, and then we would do a couch kick. And what we would start seeing is we would get motions off of our 0 position. In fact, some of our motions would be greater than a millimeter. Very troubling. Then I was definitely hyperventilating. And immediately go back to 0 degrees, do a new cone beam. The patient didn't move. And I'll talk to, the rest of this talk then will be saying what was really happening. And some of it was Vision RT. Align RT, excuse me. So again, same deal. Now it's just couch angle instead of gantry angle. We're using the MLC collimator edge, but we're going to shift our perspective. Now what we do is we're looking at the position of the sphere with respect to the collimator. I'm going to leave the gantry at 0, but now I'm going to rotate the couch. And what happens? Is there a couch walkout? You always hear about couch walkout. Well, you can use this kind of Lutz test to quantify, is there a couch walkout? Same thing with image J, but it's the same physics process, the same tool, it's just now we change perspective. We're going to watch the sphere move while the MLC is kept stationary. And this is what I saw on a true beam. This is the shift of the sphere with couch rotation in the sub-nth direction. And you can see here it's about 0.5 millimeters, 0, and then 0.5 again. So there's kind of an interesting pattern geometrically. This is what it looked like left to right, much more dramatic. And this is what's really happening. This is a Cartesian plane, sup, inf, left, right. So we're looking down from the ceiling. That's where my couch rotation point is. Notice the, well, I don't have dimensions here, but I'll get to that. So as I rotate the couch, and if I have a radiation isocenter and a Align RT isocenter there, as I rotate the couch, because this point is not at the radiation isocenter point, this is what happens to the couch. Plus 90 degrees, minus 90 degrees. You rotate off left, right, and sub-inf. Couch rotation will shift the radiation isocenter, will shift off radiation isocenter. Anything that is on that couch will shift off a radiation isocenter when you rotate the couch. You cannot avoid it. It's going to happen. And Align RT, that's where its isocenter is, its optical isocenter. It agrees with radiation isocenter, which we'll talk about a little later. But that patient, or whatever is on the couch, will rotate off of radiation isocenter as you rotate the couch, as long as the couch rotation center is not there. You can't get around it. That's a fact of life. It's a principle, it's basically a principle of mechanics and geometry. I have 3 accelerators, so I measured that couch rotation point for all 3. This was the one you just saw. Here's true beam number 2. It's sitting over here. And interestingly, the Trilogy, the oldest machine, actually has the closest coincidence of couch rotation to radiation isocenter. I thought that was quite amazing. And that's the way it goes. So the answer here is the couch rotation points are unique to each machine. And if you want to understand geometrically what's going on, you have to go and measure it. So my results will not be your results. In fact, my results are different for 3 machines in my clinic. So again, these Lutz tests show that the sphere center shifts in space with couch rotation. And this is kind of a summary. For that true beam, sub-inf was 0 to 0.5 millimeters, left to right, 0.4 millimeters. So if you rotate the couch, I'll say it again, the patient will walk off isocenter. You cannot avoid it. You may correct for it, but you can't avoid it. The cone beam CT at couch 0 is corrected 0. But that's not where the patient's going to be if you go to couch 45. Measurements with a line RT. Oh, that's right. This is an line RT meeting. Finally, right? You're all saying. The optical guidance method. Well, you set up the phantom at Isocenter. I'm going to immobilize the phantom by bolting it to the couch, and then I am going to detect movements of a 3D surface. So shifting now, this is no longer the LUTS test tool. Now this is the Align RT tool. So the first thing you got to make sure is the Align RT optical isocenter agrees with that fuzzy radiation isocenter you established, and that is done with the calibration cube. And in December 2017, there was a new method that was brought to all of our attention by the Vision RT company. And so everything I'm showing here uses that new alignment method. So I'm using the cube method that I think all of you are familiar with that do stereo. And that's how the two isocenters, optical and radiation, are made coincident. Can Align RT accurately measure the target without walkout from Isocenter? So what I did is I rotated the couch to its extremes, and then my target was in fact a styrofoam head painted flesh color, and it actually had the crevices filled, as you'll see, and it was bolted to the couch. So there's my styrofoam head. You know, bought it, I think it was 12 bucks on the internet. Painted it, filled the crevices, and I have a platform here that I made that bolts to the couch. So this mechanically fixes it, and the styrofoam head then moves with the couch. The method is you secure it, you position it just roughly with lasers or whatever. The Align RT reference image is taken, and then the couch is rotated, and Align RT coordinates are measured as you rotate the couch. And again, this is what's going to happen. Here's my little head, and with that Linac, as I rotate the couch, of course my head will go off Isocenter, and Align RT should track that. Okay. Couch shifts measured with the LUTS test or this test are transformed into the rotated Align RT reference frame. When you do Align RT work, as you rotate the reference frame, all the coordinates are with respect to the rotated frame. They're not stationary in the room. So here's what's going on. The LUTS test are the dots and the error bars, and the squares, in fact, are the Align RT measurements of, in this case, longitudinal distance versus couch angle. And what you can see here is at minus 90 degrees, you have quite a difference between what Align RT tells you and what the gold standard LUTS test tells you. On the 90-degree end, it's a lot closer. But we had a difference of about 0.4 of a millimeter. Here's what happened in the lateral direction. Now you see a large difference between Align RT and the LUTS gold standard. And this occurred at 90 degrees. So this is prior to advanced camera optimization. So there's a big difference, and this is why when we're rotating, we were seeing shifts, in some cases greater than a millimeter. So can Align RT accurately measure the target walkout? And as I mentioned, Ben Vagorn and I were talking, and he said, we're going to get advanced camera optimization in your clinic, and then make your measurements again, which meant do everything again. So it's another 3 or 4 months of work. And fortunately, Ben, thanks, you kept me working. Now what you can see is the agreement between the LUTS test gold standard and Align RT is really very good after advanced camera optimization. And then even in the worst case, the lateral direction, it is really good. Ben, wonderful. So here's the summary. Before advanced camera optimization, the differences between Align RT and LUTS test were on the order of as great as 0.6 of a millimeter, and basically those differences were dropped by a factor of 2. In fact, now we're in the range of, well, you don't really shrug your shoulders, you just know you're off 2 or 0.3 of a millimeter. Conclusion, radiation isocenter in space, I showed you that. It's plus or minus on a true beam, 0.2 of a millimeter. Couch rotation will walk you out 0.5 millimeter. Cone beam CT at couch 0 is only valid at couch 0. And then advanced camera optimization will reduce the difference between a line RT and a LUTS test by about a factor of 2. For perspective, breathing motion, you got everything perfect. And in our case, the best mask we can make, and if you have a 200, 250 pound patient, their breathing motion will be this big. Smaller patient, someone my size, we wonder if they're still breathing. You know, you don't have any motion. But big patients with a lot of mass, again, this is a perspective slide. We're talking about 0.1 of a millimeter, and breathing motion alone is now quite a bit larger, or can be quite a bit larger than the difference between a line RT and the physics LUTS test. So what do we do clinically? Real quickly, select a patient, file in a line RT. We do a preliminary alignment, actually with DICOM. You could use lasers or whatever. We refine the alignment in optical space. Then we go to X-ray space and we do a cone beam CT. Adjust the patient, X-ray space, capture a reference image, go back to optical space, and we monitor the patient. If we have a motion less than a millimeter, we keep treating. If there's some motion or something that occurs greater than a millimeter, we stop. We go back to X-ray space, do a cone beam, resume treatment. So cone beam is that's when we say, yeah, we're going to treat. But we are using the line RT as let's monitor the patient while we're treating. And that's it. So thank you all. I appreciate it.